Analysis of an unknown organic compound produces the following results. Elemental analysis by mass: carbon 73.17%, hydrogen 7.32%, oxygen 19.51%. Mass spectrum: molecular ion peak at MZ 164.0. Infrared spectrum shown below. Proton NMR in D2O is also shown. The numbers by the peaks are the relative peak areas. Use the results to suggest one possible structure for the unknown compound. Show all your reasoning. The first thing we're going to do is use the elemental analysis by mass to work out the empirical formula of our unknown organic compound. With empirical formula, what we need to do is take the percentages of each element and divide by their relative formula mass. So for carbon, that would be 73.17 divided by 12. For hydrogen, that would be 7.32 divided by 1. And for oxygen, that would be 19.51 divided by 16. Then we need to divide by the smallest. So for carbon, we would equal 6.0975. For hydrogen, we would equal 7.32. And for oxygen, we would equal 1.22. So the smallest is 1.22. So we need to do 6.0975 divided by 1.22. That equals 5. For hydrogen, we do 7.32 divided by 1.22, and that equals 6. And for oxygen, we do 1.22 divided by 1.22. That equals 1. So our empirical formula is C5H6O. Now we need to work out the molecular formula. We do this using our mass spectrum data. So firstly, we need to work out the relative formula mass of our empirical formula. So that would be 12 times 5 plus 6 plus 16, and that equals 82. But we're told that the molecular ion peak is at 164. So that would make our molecular formula twice our empirical formula. So we need to multiply by 2, and that would equal C10H12O2. Next, we need to analyse our infrared spectrometry data. So that would be stating the peaks and what they represent. So our first peak we're going to talk about is the peak at between 2,300 and 3,700 centimetres to the -1. That represents an OH group of a carboxylic acid. The peak we're talking about is here on our infrared spectrum. The second peak we need to discuss is the peak at about 1,720 centimetres to the -1, and that represents a C double bond O group. So that means that we have a carboxylic acid group present in our unknown organic compound. The peak for the carbon double bond oxygen is the smaller peak on the infrared spectrum here. Now we need to talk about our proton NMR and analyse the data that we're given here. So like with our infrared spectrum, we need to state the peaks and state what they mean. So our first peak we're going to talk about is at 1.6 ppm, and we need to discuss the splitting pattern. So the splitting pattern of this peak is a doublet splitting pattern. Our second peak is at 2.3 ppm, and its splitting pattern is a singlet splitting pattern. Then our third environment or peak is at 2.7 ppm, and its splitting pattern is a quartet splitting pattern. Finally, our fourth peak is at between 7.1 and 7.5 ppm, and it has a multiplet splitting pattern for this final peak. Using this data, we can identify the unknown organic compound. Our unknown organic compound will have a benzene ring with a CH3 group attached and a carbon with a carboxylic acid group present, a hydrogen and a CH3 group. This would give us the correct molecular formula and the correct infrared spectrum peaks. And now we're going to analyse the proton NMR peaks and where they would occur in this compound. So with this compound, we would have a singlet splitting pattern on our CH3 attached to the benzene ring because there are no hydrogens in the environment next door. Our quartet splitting pattern would be on our hydrogen of the central carbon and the side chain, and that is because there are 3 hydrogens involved in the environment next door, with our CH3 group attached to this part of the molecule. We would have a doublet splitting pattern because there's 1 hydrogen involved in the environment next door. And finally, our multiplet splitting patterns would occur on our benzene ring because they are in the right area, which is corresponding to our data sheet with the chemical shift values. The 7.1 to the 7.5 ppm values show an aromatic hydrogen. The reason why we don't have a peak for the hydrogen in the carboxylic acid group is because we have a proton NMR spectrum with D2O. That means this OH group turns into an OD group, and so the peak would disappear on our proton NMR spectrum. To get the 6 marks for this question, you must have the correct structure drawn and you must have analysed most of the data in the question.